I hurry to say that it's a bit of a tour across this field, and let's see how it goes. If I just oh no, skip. Oh dear, yeah. If I can figure out how to, yeah, there we are, to move the slides. So I'll talk about what complexity science actually is, because that's something that I find here, at least in the UK and many other places perhaps, is not entirely agreed, and it's worth to have a discussion about. So I'll say a few words about this, and then we'll move on to look at the kind of behaviors that typically arise in this sort of systems, the kind of systems that complexity science look at. And the focal point will be on intermittency and scale invariance. I'll make clear what that's about. Then we'll move after that to the important question of how to determine the probabilities for systems, so that you can start to do statistics, like in statistical mechanics, to compute the behavior of macroscopic quantities. I have this problem that it doesn't really move. Yeah, here we are. So let's say a few words about what complexity science is about. So the starting point is that the world around us is this hierarchy of processes, and this allows one, I think, to argue that complexity science, by looking at this hierarchy of processes, is both a very applied and a very fundamental science. Applied in the sense that it actually is of relevance to many different fields of science, and it's fundamental in the sense that it develops new ways of understanding the world. So how can that be? Well, there's a slide that's supposed to try to indicate that. So when you look at the different subfields, you might be a particle physicist, and then you think of well, the particles, whatever gluons and electrons and stuff, or you're an atomic physicist, and then you confine yourself to this level, and so on, microbiologists and so on. And each of these subfields don't really communicate too much with each other, right? Complexity scientists look a little bit different at things. They're not so concerned about the components. They're more concerned about how these different components at a given level. So let's take here, sociology. The components are, of course, humans and how they interact. Or if you're if you go down at particle physics, then you will say, okay, as a complexity scientist, I'm mainly interested in is the interactions between the particles. In particular, of course, in condensed matter physics, you are interested in how the interactions between the particles can lead to phase transitions and rigidity, solid versus liquid, and so on. And now when you start to look at it from this point of view, then you see that there can be commonalities, shared behavior between fields like sociology and condensed matter, for instance. There can be the question about phase transitions in the social system between a city that is segregated in, say, color, like it used to be very much the case in the United States in the 60s and 70s, and a segregation of particles on the surface. So this is the background for why complexity science can work at all, namely that it focuses on these processes that are not specifically bound to certain components, types of components. And I would say, referring to the philosopher Alfred North Whitehead, that the fundamental point to realize is that when we think of the world in terms of small components, building blocks and so on, we actually are fooling ourselves a little bit, because the point is that what is a component at one level, if you go back, if I can go back, whoops. Yeah, so what's a component at one level, say in cell biology, is of course actually consisting of a lot of different components at the level below. A molecule consists of atoms, and an atom consists of elementary particles and so on. So there isn't really any components as such, they're just collections of processes. And that's the, I would say that's the philosophical viewpoint behind complexity science. Let's move on then. Now we have said a few words about what at least I think complexity science is about, namely the study of these processes between the components and how they give rise to emergent phenomena. And of course, the systems that can support the kind of behavior we call complex systems. One should be careful not to try to define what a complex system is, because it's like biology. Biology is just one aspect, right, of a system. If you take a biological cell, then of course it both possesses biological aspects, the live aspects, or say the reproduction and so on, but definitely is also a physical system seen from another viewpoint, or chemical system and so on. So it's more a matter about which aspects of a given system you're focusing on. So today we look at one of the more, or two of the more spectacular features that you often see in complex systems, namely intermittency and scale invariance. And of course that can be represented by avalanches here. There's a dramatic snow avalanche, and scale invariance, just in case you need a reminder, is what we see here spectacularly in this Romanesque cauliflower, that the different patterns repeat themselves at different scales. So if you take, say, something like a little bit of the system and blow it up, the system looks like itself again. Of course, not all systems are scale invariant. So if you take a Formula One motor racer car, it's definitely not scale invariant. If I take a part of it and blow it up, it's not going to look like the whole, in contrast to the cauliflower. So when do we see scale invariance? Now we just notice that we don't see it always. And it's good we don't see it always. Maybe I should also emphasize that. So the reason that you can have industrial production of clothes is, of course, that we have a characteristic scale as humans, right? There is not that great variation in our sizes, where if it happened to be that there was scale invariant, then you would have humans from size 1 centimeter to maybe 50 meters tall, right? And it would be more difficult to cater in terms of size of trousers and shoes. But anyway, so where do we see scale invariance beside of the, in nature, beside of the cauliflower? Well, the place it was first studied in great detail is in phase transitions. There it happens automatically, so to say, by itself, if you take a system that can have a phase transition. So it could be, well, it could be water, but the water undergoes a different type of phase transition. But a magnet. So here is a sketch of what could be a magnet, where the magnetism of the entire system is produced by the components aligning. And what we show here is that those that are pointing out of the paper or out of the screen are red, and those that are pointing into the screen of these components are blue. And then you see at low temperature, the majority is pointing in one direction. At high temperature, there's equally many pointing in one and the other direction, because it looks like there's equally much blue and red. And then there is a separation temperature just between these, that's called the critical temperature. And what you notice by eye immediately is that here, of course, well, there is a characteristic scale, namely the entire system. If you look at the size of the red cluster, it simply fills the entire system. Up here, there's a characteristic scale again, right? They have the blobs are more or less identical size, but precisely at TC, they scale invariance in the sense that when you look closer at the figure, you see islands of red of all different kinds of sizes. So that's, of course, pretty geometrically, but that's not the most important point. The reason that it's exciting is that this.
May I interrupt just a little?
Yes, please.
I think we can see both of your slides, the current one and the next one. So it is a little bit hard to see the current slide.
Okay, so something has gone wrong here. I feared that. So that's why. Let me see if I can figure out how on earth to change this. Thank you for pointing this out, because that was definitely not the intention. Let's see. There must be a way.
Yes, now we can. Okay, so now we can see it.
How about this? Is that any better?
No, we are still able to see both of your slides.
Still. Yeah, it's. I simply don't know what is going on because I did test it out this morning on a Zoom, but it works differently now. I'm missing a button that.
In fact, now it explains everything. I mean, it's totally empty.
Let's see if this. No, how about that? Still, you see still the wrong slides.
No, either none or 2 slides.
How about if I do it like this? Do you see a slide now?
No, nothing.
You don't. Okay.
Okay, now only 1 slide.
That's it. Yeah. Okay. So now we see the same because I also see 1 slide, but that's probably better. At least we see the same slide.
Okay, this is excellent.
Good. So let's continue from here. Thank you for sorting this out. Okay, where were we? Phase transitions. Yes. So at the phase transition, the system behaves in a peculiar way. Namely, it's what we call strongly correlated. What happens in one side of the system is interdependent with what happens in one side of the system it does depend on what happens everywhere else. And that's seen in the correlation function that we plot here. So I don't know your background, so I'm trying to talk in general terms. The important point is that if I did some perturbation here, I would sense it essentially across the entire system, but only at TC. If I did a perturbation for lower temperature or higher temperature, that perturbation would die off exponentially with distance from where I did the perturbation. So this is one of the peculiar things as a consequence of the scale invariance. The other thing that's very important is that the susceptibility plotted here, the susceptibility is a measure of how much the system responds when I disturb it. So I put a small magnetic field on a piece of metal, say, and of course the metal becomes magnetic, a little bit at least, but if I do it very close to the phase transition of the magnetic phase transition, then the response is infinite, it diverges. So the two things that makes a scale invariant critical state very peculiar is this, that it's correlated across the entire system, everything is really strongly influencing each other, and that it's a very susceptible system. Now, these are the equilibrium statistical mechanics systems, and you need to, the state comes about naturally, but you need to put the temperature at TC, and that's of course a bit special. So the situation then becomes more interesting if you could argue that that this critical state arises by itself. I need to jump a little bit forward and backwards here. So this was this suggestion that it's not only when you tune as a parameter to a specific value, like the temperature to TC, that you get criticality. This was suggested by 3 physicists, Bach, Tang, and Wiesenfeld, a long time ago, back in 1987. And they came up with something they call a sandpile model, which is just a computer model, a cellular automata. And what they showed was that when you have some algorithm that says that you drop grains down, so you build up these staircases, and if the steps become too steep, then it corresponds to a too steep slope in a real sand pile, and you need to redistribute, so you let sand slide down. And then what they showed that for this cellular automata, the computer model, the size of the avalanches that you induce by randomly adding sand have no specific scale. So they, what we call power law distributed, they don't have an average size, for instance, because there are too many big ones. The probability for finding an avalanche of a certain size decays like the size to some negative power, but to a small negative power, so small that the moments don't exist. So this they call self-organized criticality. I should hurry and say, unfortunately, a real sand pile doesn't work like this, but there are other systems that work like that. At least tends to somewhat work like this. Small sand piles or sand piles that are rather piles where the gravitational force can be small. So rice piles, this was studied in Norway, where they looked at rice, which is light compared to the mutual friction forces between them, and they showed that they got avalanches of rice that follow this kind of scale invariant distribution for quite a dynamical range. What we call superconducting avalanches in type 2 superconductors, that's the magnetic rearrangement inside the superconductors that follow something like this. Forest fires, epidemics like measles outbreaks, rain events, brain activity, and size of financial crashes. So clearly there's something about this that makes it interesting. And we'll get back to the rain and brain in a moment. But I just want to mention that the philosophy of the self-organized criticality was that you drive the system at certain low rate, putting in sand every so often, and then you see how you build up and suddenly you release intermittently once in a while some big event, but the system is in a stationary state. That was the philosophy. Now we go back to this slide here, and then I remind you that of course there are many systems that are not in stationary states, and therefore we'll, after having discussed these avalanches a little bit and self-organized criticality, we'll go to something we call record dynamics, which is where you have a system that gradually relaxes. And then you also have intermittency. But that intermittency is of a somewhat different nature from the self-organized criticality intermittency. And you don't necessarily have scaling variance. But we'll get back to that. Just to make clear from the beginning that certainly intermittency is a very prominent dynamical feature of complex systems, but it can come in different versions. So let's move on, go back to the self-organized criticality sort of philosophy and look at something that is quite neat in terms of demonstrating what I want to argue, namely that complexity science is able to identify commonalities across very different systems. So here is this is not something I've done, I'm just referring to some studies where they have looked at precipitation, rain, and activities in the brain. And what they find is here, this study of rain, that's Ole Peters and Healing and somebody called Christensen, Kim Christensen. Number of people have been involved, but Ole Peters is the sort of the recurrent person. What we want to look at is that if you plot the amount of rain in a shower, how much rain actually hits the earth, and how often you have a shower of that size. So this is this distribution of shower sizes. Then you see in a log plot, you get scale invariance. So it's like these avalanches that scale invariant. By that we mean that it follows power laws, right? So rain does that. Now over here, this is work by Dan Gialvo and his group in Buenos Aires. This is now a brain. Took a brain, stuck it into a fMRI scanner, and then they look at the activities in the brain. And this picture shows how many boxes, that's the small compartments that the scanner divides the brain into, small cubes of size a few millimeters on each edge. And then they say that, then they look at how much how many voxels are excited, and then they find also a power law relation. But it goes so okay. So now we can say, that's very good. Now brain and brain has this kind of shared property that you see power law distributions of the event sizes. But it goes further than that, because Ole Peters and co-workers looked at how likely is it that if you go and check the humidity of the atmosphere, that it's close to the humidity that allows precipitation to occur, rain to fall. And that's this blue curve here. And you see that the atmosphere has this peak around the precipitation. The red curve is onset of rain. So you see it's peak around where the rain sets in. Danzig, Jalvo, and co-workers did the same for the brain. And here the blue curve is also the peak in the activity. And you see that's also peaked to some extent around where the activity sets in, the red curve also. And I should also mention that there are models that behave like this, that you just drive them continuously. They spend most of the time in a region where the event sizes turn out to be power law distributed, and the system itself, by just being driven continuously in a homogeneous way, organized it so that it spends most time in this critical region, if you like, critical in the sense that the system exhibits scale invariant behavior. So I found that's very neat. But on the other hand, you also noticed, of course, that these are not really strict power laws, and when you look closer, it's maybe not it's not entirely like in an ideal statistical mechanics setting up in terms of statistical mechanics models where you have infinite scaling range and so on. But nevertheless, there seems certainly to be something about the scale invariance. Now, this is, of course, probing scale invariance by looking at event sizes. That's just one way of doing it. You could, in terms of what I said about the, let's jump to the back and remember that when statistical mechanicians look at scale invariance, they actually study the correlation functions and try to compute that or measure it. And they don't look at avalanches, because the correlation function is much more directly related to spatial and temporal dependencies. So can you do the same for the brain? Yes, long time ago, we did that here at Imperial, and had people in scanners and looked at the activity in the brain and looked at the correlation function of the activity of voxel I at time t, and make this correlation matrix then. How much activity at voxel I is related or correlated with activity at voxel j. And then you measure the correlation function, and when you plot it in a log plot, you see you get scale invariance. So actually, the brain is not only scale invariant in terms of its activity, as looked at by Dante Jalvo, but it's also directly the scale invariance shows directly up in the correlation function. That's in space. You can also do it in time, and the correlation function in time Fourier transformed gives you the power spectrum. And if the power spectrum is close to a 1 over frequency dependent, which is what this graph shows it is, then you also have a correlation function in time that behaves algebraically. So, conclusion that definitely the brain and rain shows scale invariant features in activity, but the brain also does it in terms of correlation functions. So that just confirms the idea of self-organized criticality, that there are maybe a typical type of behavior here where systems organize themselves into some kind of critical state. But as I said before, not all states are, of course, stationary. You have many situations in nature where you're looking at things relaxing. So I mentioned first here relaxation of spin glasses. That's not something you see in daily life, perhaps, but you see something similar to that. When you take some system and cool it down rapidly, then it gradually relaxes into the low energy state at low temperature. And there's lots of experimental work on something called spin glasses that are magnetic systems. It's called glasses because, like ordinary window glass and other glasses, the material, the arrangement of the material in terms of magnetic moments becomes inhomogeneous. Then there is this magnetic relaxation of superconductors. That's where you take a superconductor and suddenly turn on a field, for instance, then the magnetic field gradually relaxes into the material. And that's also a non-stationary process. To go to some completely different situations, we can think of evolutionary ecology. So the fossil record is showing a intermittent relaxation, in the sense, of course, we have the intermittency are the great extinctions and creation events that you see in the fossil record, and that's for a long time been documented to exhibit scale invariant behavior in time and size. But what's also important is that it's not a stationary process. Since the Cambrian explosion 650 million years ago, the extinction rate, the rate with which these mass extinctions occur, has slowed down. So it actually happens more and more seldom. Of course, unfortunately, humans seems to have are in the middle of creating one of the largest mass extinctions ever. But before that, just a few hundred years ago, before that, you could say that this is the then there is the Orimori aftershock law from earthquakes. You see, this is really complexity science because you see shares systemic behavior that spans totally, completely different systems. And again, I emphasize the reason this can be is because you would imagine, as a scientist, that it's not that the components are shared. Hungry ant has very little to do with the superconductor, but the way that they interact might actually have shared properties. So let us look at this kind of relaxation. We call it record dynamics, as will be clear in a second. But what's the fingerprint? What's to look out for? So the non-stationarity is indicated here to the left. So you see these are actually events where an ant leaves the nest, and the experimenter has simply put a red line at that time when an ant left. And you see they are not stationary, right? Because it's more and more seldom that ants leave. When you plot this at a linear size, you see the spacing between the red bars becomes bigger and bigger because it becomes more and more seldom that an ant bother to leave. But if you take the logarithm of the time axis, then you see immediately your naked eye that this is something that becomes stationary. Now it's like a Poisson process where, of course, there are fluctuations, but there is essentially the same amount of activity in this end of the time axis as in that end of the time axis. So how could that, what kind of mathematics could be behind that? Let's see if I can navigate here. There's, well, record statistics might be an explanation behind this. So what is record statistics? Record statistics comes, I think, actually first was motivated by Cambridge mathematicians who were, of course, as they had to be, keen on cricket and wanted to figure out what is the likelihood of a new record in some sort of cricket game. So, or long jump, what is the probability that the next jumper will actually manage to jump longer than anybody else? Mathematically, what you do is that you take, at each time step, you draw a number, that's these red balls, And you see they can take different values, and they are equidistant, right? Every time that there is a new red board. Now you construct the record out of this, namely, that's this staircase, where the first time you draw a number, that's per definition the first record. And then you see here, we're lucky already the next one to get a value that was bigger than the first one. So this is now the new record. That stays the record because when we draw a number the third and the fourth time, they are actually below this value. So that's the record until here. When we draw the fifth number, that happens by accident to be bigger, and so on. So the record times are those time steps whenever you manage to draw a number that's bigger than anything you've drawn so far. And then mathematicians will be eager to study what is the statistics of this time series here, where the records happen. And the beauty of this is that the statistical properties of the T1, T2, and so on, the record times, are completely independent of the statistics of the individual drawers. You see immediately, of course, that you need to have a situation where you have infinitely many possible values for the individual drawer. If you did this on throwing die, then of course, since the maximum would be 6, well, you'll pretty soon run out of records. But if you have a random number generator that can put out infinitely many numbers, then you can continue doing this as long as you like. See, when I hesitate, it's because I have absolutely no idea where I am, because we see exactly the same one. Yeah, there we are. So you can do this, you can do the mathematics of this, and maybe I shouldn't go into too much detail, but the point is that all what you need to assume is that the individual drawers are independent. So what happens here, it doesn't depend on that. So you're just looking at the probability that you manage to draw something, pull a number out that's bigger than before. And then you can easily do the mathematics, and what you find is, conclusion, that this process, the time instances at which you draw new records, is a Poisson process in logarithmic time. This was what we saw here, that you get, as soon as you take the logarithm of the time axis, you get a homogeneous stochastic process. So certainly the ants fulfill that. The mathematics that leads to this is just that simple drawing numbers and take the largest. And since it's a Poisson process in logarithmic time, then of course it fulfills the properties of a Poisson process, where you know the average number of events is proportional to time. Now, well, it has to be proportional to logarithmic time. The variance is proportional to logarithmic time, because all what has happened is that we replace time by logarithmic time. This means something immediately. The rate of records is constant in logarithmic time, but that means, of course, that they decays, and they decay like 1 over t, 1 over the time. Otherwise, they wouldn't be stationary in logarithmic time. So let's look at a peculiar example of this. An ant colony study at Bristol University some 10 years ago, and what they do is that they have this peculiar type of small ants that likes to live in a nest, and they're very clean animals, so they don't bring a depot, or they don't bring more food into the nest than they actually eat. Which means, so they don't store the food in the nest, which means that every so often they get hungry. They need to send an ant out to look for food, which you see here is happening. And she finds something, like lots of good food. And then the idea is that that scout that's out looking for food brings a little bit of food back and shares it. That's how they normally operate. Now the experimenters, Richardson, Robinson, Christensen, well, I was also involved, but I didn't do any experiments, and 2 times Franks, did the following. They actually snatched the ant that came out to look for food and didn't allow it to go back into the nest. And then the situation becomes that this is where this time record came from. Then what happens is, of course, that the ants still sitting in the nest realize that they didn't get any food, right? They become hungry and they need to send another one out to look for food. And every time they send another one out, the experimentalists make a red bar and do the statistics of this. And then they find that the statistics is precisely like this log-Poisson process. So hungry ants seems to follow record statistics. You can see here the accumulated number of ants. So they did lots of small colonies, colony 1, 2, 3, up to 7. They actually need more, but they're not all here. And what you see is that on a logarithmic time scale, the number of ants who have left the nest is more or less linear. Right, so that's a good indication that it follows this kind of record dynamics. Another system that I want to point out is earthquakes. So we all know, of course, how earthquakes work, that you drive the tectonic plates very slowly, and then once in a while, the stress that has been generated is suddenly released. And you probably also all know, have heard about the Omori aftershock law, which was established by the Japanese geophysicist Omori, 1890s, I think it is. And what it says is that if you take the number of shocks after a given shock, the number of new earthquakes after a given earthquake, it decays like 1 over time. So that sounds very much like what we just were talking about, right? Because in record dynamics, you have this decay. But now, there's more to it. I also mentioned that it doesn't matter how the statistics of the underlying stochastic variable is, you should get the same kind of behavior. And that, of course, would suggest that you get the same kind of behavior no matter whether you have had a big shock or a small shock. And here, what I've taken, I've taken a figure from a paper by 2 Frenchmen, Young and Sonnet, where they wanted to say that the Omori aftershock law is index dependent. It depends on the magnitude, and that's the blue line. Then these turquoise lines are just 1 over time parallel transported. They're all parallel, and you make up your mind whether you think the blue lines fits more accurately than the turquoise. The turquoise line would be those you expect if it's an underlying record dynamics process where the fluctuations don't matter. Okay. So now we shift gear. If there are any questions to this part, maybe we should take them. No? Then let's jump. I promised you in the outline that we're going to think a bit about how you can actually find the probabilities for a given system. By that I mean, what you really like is to have the probability to find the system in a given state, right? And in statistical mechanics and many other areas, max entropy principle has been extremely successful. And one can show that, well, that was what James did in the 50s, that the traditional Boltzmann-Gibbs and actually also Shannon, but Shannon, of course, did coding theory, whereas Boltzmann and Gibbs did physics, the systems, that the statistical mechanics developed by Boltzmann and Gibbs can be derived from a maximum of entropy. There are tons of entropies. So, of course, the Boltzmann, Gibbs, Shannon entropy are those that we're most familiar with if we do statistical mechanics or information theory. But there are Rayleigh, like Hanel and Turner and Gell-Mann and many, many, many more. Total zoo of entropies. And that's, of course, a bit of a problem because which one would you use if you now say that I want to do the following? I want to find the probabilities of my system by maximizing an entropy, because that's been such a successful avenue in statistical mechanics. Yeah, then I need to figure out which entropy I should maximize. So there's actually words about the role of entropy in statistical mechanics. entropy was introduced by Rudolf Julius Emanuel Clausius and Clausius in 1862 as heat transport, really. So entropy in Clausius thermodynamics is given simply by the amount of heat exchanged divided by the temperature at which you exchange the heat. So that's something you can feel with your fingers, so to say. Then Gibbs and Boltzmann, and later on Shannon, but Shannon didn't know what he was doing in terms of statistical mechanics. That was Van Neumann who told him that it looks like statistical mechanics. So it's really Gibbs and Boltzmann who wanted to make a connection between this mathematical expression and Clausius' thermodynamics expression. This is, what does this say? It says that the probability for finding your system in a state number I, you can use that to construct an entropy by this mathematical expression. So you take logarithm, and what you could say is that the entropy is actually just the average of minus the logarithm of these probabilities. And what Boltzmann mentioned was that this, if you're in equilibrium, have that all states are equally likely, then this entropy has the same properties as the Clausius entropy and the second law of thermodynamics, namely that it moves towards a maximum in equilibrium. So that's the argument for why this mathematical expression might have something to do with this mathematical expression, where here you have heat and stuff, right, and here your probabilities. Now, so what is it good for? Well, if you just assume that this is the somehow God-given, or whoever gave us it, James or Boltzmann or whatever, entropy, then you can find the probability. You just maximize this. But because whenever you maximize something, you do it under constraints, and then the different constraints that you put on. The most natural, the one you cannot avoid is that the probabilities add up to 1. So if you maximize this expression under the condition that the sum of the PIs is equal to 1, then you get what is in statistical mechanics called the microcanonical ensemble. That is simply that all states are equally likely. W is the number of values that I can assume, so the number of different states of the system. Now, if you say that you somehow can control the average energy, so you want to maximize this, but you want to have this constraint, that the average of the energy is equal to some fixed number that you put on, then you get what is called the canonical or the Boltzmann weights. And that's, of course, beautiful and fantastically efficient and being used tremendously in statistical mechanics. Okay, so the role of entropy is that it enters into thermodynamics and that it can be used as a ray device to find the probability. But you then need to think a little bit about extensivity. When you look at this expression, it looks like, well, it must be extensive, right? Because the amount of heat I need to pump into a system will be proportional to how big the system is in order to get a given change of temperature, for instance. So at least the change in entropy is extensive. That's one thing. Also, that when you take the Boltzmann expression for entropy and evaluate it on a system where you have n particles that each can be in k states, so that together they can be in k to the n states, then you also get that it's extensive. But I should, of course, make clear what I mean by extensive. I simply mean that the dependence of the entropy on the number of components for many components, that's what I write here, is proportional to the components. So it's asymptotically linear. And it means it allows you to define an entropy density, right? And take the thermodynamic limit, as we call it. So if I divide by n, I get that S, the entropy of n components divided by n, is independent of the number of components. So when I take the limit n going to infinity, I get a number. That's it. That's well defined. And that's how you deal with statistical mechanics systems, because you have systems that have a number of components of size 10 to the 26 Avogadro's number, right? And therefore, you feel that you're pretty close to the infinite limit. So it means that when we deal with entropy, it seems like extensivity is very important. And Constantinos Thallis, as some of us, a person, I don't know how many of you know him, he's a fantastic statistical mechanician from Rio de Janeiro. And he has started back from the late 80s an entire industry of doing or generalized statistical mechanics using his entropy that looks like this. So this is, of course, it looks quite different from that, but the idea is that this should be particularly good if you have systems that are strongly correlated or complex. And you see that there is a Q parameter here, and the way you determine Q is so that you make sure that the entropy is extensive. And then Constantino have showed convincingly that if you use this, but that's your straight mathematics. If you maximize this, then you get something called Q exponentials. And what he has shown convincingly is that these Q exponentials as distributions for probabilities shows up so many places that you can hardly believe it. Constantino can talk for hours about how you find Q exponential distributions in hadron collide condition of transfers, momentum transfer in hadron colliders, or in outer space, or in mammograms, or all over the place. So that's very peculiar. And of course, Constantino would say that, oh, that's lovely, because if I find the distributions, the Q exponentials that I get by maximizing this entropy, then it's probably because this entropy is of fantastic relevance to all sorts of systems. And this is maybe a wrong conclusion. What is not wrong is that the Q exponentials are very relevant. But let's take a look. So what we now want to do is to think of systems where the standard Boltzmann, Shannon, Gibbs kind of dependence on the total number of states of the system for n components is not exponential. So this, of course, is the kind of thing you get if you throw coins. They can have head and tail, and if they don't influence each other, then obviously each of them can be in two states. And if you have n of them, then you can have 2 to the n possible configurations. But then when you start to think of complex systems, then emergence, new phenomena happen. That's precisely the idea of a complex system, that the system, that the components of the system allow new behavior that the individual components don't exhibit. And this can lead to different types of functional dependence of W on K. You could have very strong dependence between the system, between the components. So the most extreme would be that all the other coins will have to show the same face as the first coin you throw. Well, then in that case, then W of n always 2, right? No matter how many n's how many coins you have, because the first one will determine what comes out. Or you can have, and of course that's a totally fantastic extreme case, but you can imagine that strong interdependence limits the number of configurations that the system can be in, so that W becomes algebraically dependent on n rather than exponential. But you could also have this situation here where the new states can be created. That's really emergent, right? So what we try to indicate here is that you can throw the coins and you have the 4. If you have 2 coins, you have those 4 where they have head, 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 tail, tail, head, and tail, tail. But then you allow another one because they can actually glue together and then they can suddenly stand on the edge. It's not tremendously important precisely how you make a new state. The important point is that somehow these components can go together and create a new state. And if you're a chemist, you would say, of course, that's what happens all the time. Take 2 hydrogen atoms and let them get close to each other, and they'll form a hydrogen molecule, which is a completely new entity that has that you cannot deduce the properties of those. You cannot deduce from the individual hydrogen atoms. So then you get that there are certainly many more states, right? Because if you take this, we call this the pairing model, and you can compute the number of allowed states, and it goes like n to some constant times n, so much faster than exponential. Now you're in the situation that you want to find an entropy that can handle these different growth rates of the number of individuals, of the number of states of the system. But you also want to have that it fulfill the requirements of probability, namely that if you, let me go to here, if I have two systems, A and B, each of them can be, they can have a W, whatever they like. It could be a Boltzmann, it could be an algebraic dependence or a super exponential. But now I take them and just put them next to each other. And I don't let them interact. I just consider them formally either as a total system or two individual systems. Then, of course, the laws of probability tells me that the probability of the combined system is just the product of probability. So I can use, or rather, I should say that it's not me. It's Pier Giulio Tempesta, a phenomenal mathematical physicist that works in Madrid. He's an Italian from the south of Italy and now works in Madrid. Has used these observations to find a requirement for how you compose systems. So of course, in general, you don't know how to compose systems because there could be interactions. But you can say that if I just formally look at it as two, either as two independent systems or as one whole, then I can just do mathematics and use the laws of probability. And that puts some restrictions on how the entropy, on the functional properties of the entropy. For instance, it doesn't matter which order I do things. So it has to be cumulative. The entropy has to be cumulative. It has to be associative. Also, so I get some rules, and you smell immediately. You can see immediately where we're going, right? Because when you have something that has to do with combining things and fulfill some rules, like commutation or associative relationships, then you'll get towards groups. There is a theory of formal groups that you then can make use of, and that actually allows you then to suggest entropies of this form, where the entropy is a functional, like any other entropy, of the individual probabilities of the different states of the system. And then this G, that's a formal group generator. So how do you find the formal group generator? You find it by insisting on your entropy to be extensive on the uniform ensemble, when all the PIs are equal, meaning that for, well, this is for large n, you want it to be proportional to n. Then, since you start out in order to fulfill all the composability requirements with a structure like that, then the game is now, can we actually determine G by insisting on extensivity? If we know how W of n behaves. So let's take an example. Assume this super exponential, but it could be sub-exponential, it could be exponential, it could be whatever. All what we now need to do is to call this variable in here for t, and then you invert around, and what you find is that the group generator is given in terms of the inverse relationship between number of states and number of components. And voila, there you are. So now you get an entropy which functional form is determined precisely by which W you have. So if it's Constantino-Zales stuff, then W would correspond to n to some exponent A algebraic behavior. If it's Boltzmann, then W is k to some n exponential behavior. And if you create new states, then you have this super exponential. And you can see then, of course, you get different types of entropies. Forget about this trace form for the moment. We can give another talk on this at another time. The most general is this column. And you see what I said was that you can have algebraic, exponential, super exponential, and you find entropies that depends on or given directly by how the number of states relates to the number of components. And of course, they are very different. Constantinus sits here, but it's sort of exactly the same as that one in a certain limit. So that's not so essential. The essential point is that Constantinus' entropy, Constantinus-Thiele's entropy, corresponds to the algebraic behavior. Now we say, oh, but what is that well behaved? Is it good for anything? Let's consider this max entropy example. And when you do the maximization, either under normalization, and of course, again, you just get PIs are uniform, or you put on some constraint on the average. And what is amazing then is that you get the Q exponentials. So they look like this, these functional forms. Q exponentials, the one that Constantino have been fitting to all over the place. But the point to make clear is that this happens also, it happens definitely if you have W algebraic, like in Constantinus-Thiele's case, but you also get the same form if you have super exponential. The only situation where you don't get it is in the Boltzmann case, where W depends exponentially on the number of components. So maybe this is the reason why you see Q exponentials so widespread. You don't need to convince people first that it's your system has this very confined set of states. It could equally well be that your system has a huge number of states that goes faster than exponential. You'll get the same kind of probability weights. So we need to finish. The summary is that by focusing on how the number of states depend on the number of components, you can handle the standard Boltzmann ensembles corresponding to exponential, and you can handle complex systems where when you put the component together, they change the number of available states away from the exponential, either limited to only algebraic, say, or to super exponential. And then you use these group entropies, and you find that when you do max entropy, you always get the Q exponentials. Overall conclusion is that, well, complexity science is a general study across all different scientific fields of the generalities of how emergent properties behave, and they can show amazing similarities across systems that are totally different, like rain and wind. The two very much seen aspects of emergence is intermittency and scale invariance, and then we're just starting to try to figure out ways to determine the probabilistic weights you need in order to do the mathematics of computing how the systems behave. And these group entropies that Pier Giulio Tempesta have pioneered seem to be tremendously exciting in this respect. Thank you. And I put some overall references. If anybody are interested, well, you can, you can contact me or I don't know, this was recorded, I believe. So then you can just go and look at the references here at the last few graphs. Thank you.
Thank you very much, Professor Jensen. Thank you very much. Now, if you are okay, we will proceed with the questions.
Yes, please.
Any questions? You can just have your mic open, unmute, and if you want, you can also turn your camera on and ask your question.
Sir?
Yes.
Hello. This is Alican from Mersin University. Thank you very much for your beautiful talk. I want to ask a question about scale invariance in activity in human brain. How did you decide that?
So there are two complementary ways of doing it. In the brain experiment by Dante Calvo's group in Buenos Aires, they did fMRI, so you know these big scanners, and they measured the amount of activity. And what is surprising perhaps is that the brain has bursts of activity. When you follow the brain activity in a scanner, you see that there are quiet periods, and then suddenly bursts of activity, quiet period, and that goes on. And that then led to this distribution of event sizes that goes algebraically. You can also go down at the tissue level. This is an experiment by Plint's long time ago, 20 years ago actually, at the National Institute of Health in US, where they looked at tissue extracts from rats and saw the same thing, but of course at completely different scale. They look at the individual firings of the neurons, whereas here you have thousands and thousands of firings. So that's one way of doing it. The other one was what we did at Imperial, where we looked, oh dear, he wants me to take a break all the time, where we looked at the correlation function in time and space of the activity detected by the fMRI scanner.
Mm-hmm.
And then you find that the correlations exhibit this kind of power law.
Yeah.
Does that explain it?
Thank you.
Any other questions?
Thank you, sir.
Any other questions? Okay, I have a question.
I have a question, Barış Hocam. Sorry.
Buyurun Onur Hocam.
Dear Professor, thank you very much for this nice talk, actually. Let me give an example before my question. What I remember from a TED talk about ant colonies is that most of the members of the colony has some special tasks, but a significant number of them has no such particular task, but their how can I say that? They have a contextual nature, by which I mean that, for example, if the colony needs more cleaner ants, then they become a cleaner, or
Mhm.
if the colony needs more hunter, then they can become hunter.
Yes.
They are able to do some multitask jobs, but if there is no situation, then they can only go around without any particular job. Then it means that I think if we try to describe them by probabilities, we cannot use joint probabilities, which are the product of the marginals.
Good point. Yeah.
Since they are contextual, or they share correlations, or we can also interpret this in this way, I think. Also, you mentioned about molecular systems. For example, in a hydrogen molecule, the electrons become correlated once again, and because of this, we cannot describe reduced states of these electrons without the knowledge of the other ones, and they become correlated in any way. Yeah. I think this kind of systems, the total system, the entropy of the total system is not extensive because of these correlations or contextuality.
That's absolutely correct. Yeah.
And but also
I'll answer that first, because that's essential. Then you can continue afterwards. So let me just say that this is entirely spot on. That's the observation. If you by entropy mean the Boltzmann, Shannon, Gibson, that will definitely not be extensive on these systems where you either have fewer states or many more states than just the Cartesian independent combination. So that's why the philosophy of this group entropy approach is to say that, okay, but you want to have an entropy that is extensive. So you need to give up on Boltzmann, Shannon's entropy in this case, and then construct another entropy that even on these non-exponential cases can remain extensive.
I see. And actually, my question was related with that, but I think you give the answer before I complete the question. Thank you very much.
Okay, thank you.
Okay, any other questions? Any other questions? Okay, then
So
I have,
if
okay, yes.
Is there an upper limit for the measure of complexity defined by the entropy?
Very nice. No, there isn't really. Let me just unskip here. So we can actually use this formalism of the group entropies to define a measure of complexity. Because the point is that the composability, which we use in order to have a mathematical restriction on the mathematical form or the functional form of the entropy, we can use this, if you look at this line here, to define a complexity measure. And that's the deviation between the actual fully interacting. So let's say that let's think in terms of hydrogen, just for argument's sake, that you put hydrogen in A and hydrogen in B, and as long as they are in each container, each their own container, then of course you won't make molecules from an hydrogen atom here with an hydrogen atom there. They'll just be separate. And that's what this entropy tells you. That's why you're using Cartesian product, because they're not really interacting. But if you now remove the barrier and then suddenly they are one big gas, then of course it'll be different. Then it's this system. And then the deviation between the actual fully interacting whole and the one that's just the Cartesian product, the entropy difference here, you can use as a measure of complexity. So this is 0 if you have the Boltzmann case, because then these two, the fully interacting and the Cartesian product, is the same. And you can then look at it for different, so delta take different functional forms depending on whether you have algebraic or super exponential. So as I said, it's 0 for the Boltzmann, but it depends on the number of components in different ways. Yeah, but there isn't. There's at least from this approach, there's no upper limit on how complex you can make it.
Okay, thank you.
Any other questions? Any other questions? So then I have two
Shall
questions.
I ask one more question, Barış Hocam?
Onur Hocam buyurun.
You have just showed the complexity measure in terms of the entropies. Actually, if we use the Shannon entropy in this definition, it gives it becomes equal to the mutual information. Am I right?
I don't think so.
Because in mutual information, we first take the product of the sub-entropies, then we extract the joint entropy. It seems very similar.
It is similar, but it has to do with how you combine the system. So in Shannon's case, which is of course equivalent to the Boltzmann and Gibbs, you have the exponential dependence, and therefore these measures that we do here would be 0. So it's a bit of a sledgehammer, it's a really brutal way of measuring complexity, because it will say that all systems that are described by Shannon entropy have complexity 0. And I realize that that's maybe an over dramatic way of stating things, because yes, of course, there are tons of different complexity measures also for that kind of system. So I think of this as a meta classes, where of course you can go in and focus on each class and use more elaborate mathematics in order to distinguish between the degree of complexity within a class. And there you would use mutual information as one example, or many other of these in this class. But the point is that you cannot just use the Shannon or Gibbs-Boltzmann entropy to handle these other cases, right? Because definitely in information theory, you like to have an extensive measure. Otherwise, you can't define the entropy rate. and you have systems that either behave like this or like that, so either algebraic or super exponential, your Shannon entropy would not be extensive, and you could, for instance, not define the entropy rate.
I see. But let me ask my question. Do you think, is there any relation between the correlation and complexity? Because these complexity measures are also used in the quantification of correlations in, for example, quantum information theory or other similar theories.
Yes.
Could you give your opinions about this relation?
No, there's no doubt. I agree entirely with what you say. That of course the correlations are really closely related to the degree of complexity in a system. Maybe I should point out that if you are interested, you should take a look at what Giulio Tempesta recently have done in terms of using the group entropies to characterize time series. So relating to permutation entropies there. And of course, they also, these group entropies are also used in quantum mechanics, like the Rayleigh entropy, in order to quantify the degree of entanglement. So you're absolutely right. So what I'm talking about is really a brutal way of classifying. That's what I tried to say before. This is very big classes that you get by defining them, defining the classes depending on just the way the number of states are depending on n. Within each state, within each class of systems, you can definitely imagine that you have better ways of distinguishing the amount of correlation or complexity inside a class. This is of course what people have done for a long time for this class, where you have the Shannon entropy.
Okay.
So just I try to make precisely clear what I try to say. The ability of this measure is to be able to distinguish these very strong differences when the correlations, interdependencies in the system are so strong that you simply change the number of available states. The weakness of this measure is that it says, oh, anything that has exponential dependence on state has complexity 0. I realize that's going a little bit too far, right? Because all the work at Shannon and mutual information and that kind of stuff is precisely to elaborate on the degree of complexity within this kind of class.
Okay.
Thank you very much.
Onur, do you have more questions?
No, hocam.
Okay, then I can ask.
Please continue.
So, Professor Jensen, I have one remark, one question.
Okay.
You know, Tempesta's paper, especially the first 3-4 papers,
Yes.
it covers a very wide territory.
Yes.
I mean, really wide. It's very general.
Yeah.
Then 4 years ago, I don't know if you have seen the paper, but we have checked whether Tempesta's framework, how well it would do if we compare it to third law of thermodynamics.
Okay. Yeah.
So we have seen that many of them fails. So that there is a narrower, I mean, not only Shannon, of course, but there's a narrower circle of entropies left.
Okay.
If you want to connect it to thermodynamics, and when you look at the thermodynamic laws, they fall one by one, many of them. That's a remark. It's already published in Annals of Physics, I guess. And my question is the following. This is something very simple. Everybody presents it. I also talk about it, but I never understood really. Let us say we have two systems. with probability of the whole thing, and then you have those different subsystems A and B. Yes, yes. Here, the composition PAB is equal to PA times PB, right? So you have two independent systems, but then, for example, for Salis, even for independent systems, there is a correlation, you know, because SQA plus SQB plus 1 minus Q SQA times SQB.
Yes.
There is a correlation. How should we understand that even for two independent systems, we have a correlation of some sort? How do you?
I think so. The way I see it is that it depends on what you mean by independence. So when I use the term simply, and the term independence I use to mean this, that the probability factors.
Exactly the same, yes.
Yeah.
So two things are probabilistically independent.
Yeah.
But then their entropy is correlated. So imagine that you have two coins. They are separated, they don't interact, they are independent, like two different people tossing them.
Yes.
And then at the end of the process, you look at their entropies and you say that there is a correlation.
Yeah, but I think it has to do with what I'm trying to say here, where that there are two ways I can think of combining systems. I don't have a good graph. So here it's a pure formality. I just let the two systems sit next to each other, and one decide to look at them as a whole, and the other one look at them as two separate systems. And therefore the probabilities are like this. But that's not the same as if I now remove the barrier between them. As soon as I remove the barrier between them, then this doesn't hold any longer. Then the probabilities are not products any longer. Then you form, in the terms of the hydrogen, right? Then you start to form molecules across the two. And I think
I fully agree. My point is the following.
Yeah.
For example, when you take Salis entropy, you have this condition, PAB equal to PA times PB.
Yes.
You have it. But in the entropies, you don't have it. I mean, in the entropy expression, you have correlation. So even for independence, like your figure on the left, A and B, is one system, it's okay. But when you separate them, somehow there's correlation.
I see. But I wouldn't use entropy to determine independence, right? I would use probability product as the definition of independence.
Yeah. I mean, in terms of probabilities, we can say independent, right?
Yeah.
But in terms of, for example, in quantum mechanics, they use it as a correlation. Then if I use, because it's a tensor product there.
Yes.
So you use tensor product, but then right-hand side of the equality in terms of entropies, you have correlation.
But that is for the fully interacting system. That's where the some particle or whatever components can see each other.
I mean, this I always try to understand better, but I never succeeded.
But the Salis entropy corresponds to the algebraic case, right? To here, to this situation, where the number of states only grow very slowly. So clearly, there is enormous interdependence between the components.
Okay. Now I see. Okay. That's very helpful. Thank you.
It's only in the Boltzmann case that you can have consistency, so to say, between the number of states and just a Cartesian combination.
I mean, it's so easy to get used to the usual Shannon-Boltzmann way. You see, I mean, It's
And
like
I think Constantinus Thales for years and years has always alluded to this, but of course, he's never derived his entropy from this condition.
yeah, that's true. Yes.
This is Per Giolius' contribution.
Yes,
That he
that's
assuming.
that's true. Yes. And another question now, scaling invariance scaling invariance in a way implies power law, because you see it's the distribution that gives scaling invariance. But is it always the case that when we have such a scale invariance, we always end up with the power law?
I would immediately say yes, but I don't think the other way around necessarily work. That you can conclude from power laws to scale invariance.
That's certainly true. But what about the other way around?
Yeah, I would just intuitively say I thought, because if I have scale, sure, I don't know if you can see that the screen goes black because it wants me to take a break. Anyway, I won't take a break. And yeah, I just think of it in terms of fractals, right? Because if you have, if either space or time, if I have the same structures repeated itself at all scales, I would think that I can't avoid power laws.
In fact, at the end, it's renormalization theory, right?
Yeah, that's right. That's clearly the underlying, that's the Migdal Kadanoff kind of approach to it.
Thank you very much. And there's a question from chat part. How do we know which of the two interconnected systems we are investigating? For example, the entropy of food in the forest rather than the entropy of ants.
Yeah, no, that's a very good question, actually. I maybe I can rephrase it, because if I can tell you, just because we're friends, we wanted to test this measure of complexity on the brain, right? Because you think that the brain must surely be something strongly complex and probably have the exponential, faster than exponential growth of number of states. But then after fiddling with it for a while, we realized, of course, we cannot do it, because you cannot break the brain into the Cartesian product. No one volunteers for that, right? Because that would mean that you took the two halves and separated them. And so we are in this, we have this dilemma that we can write it down mathematically, but we wouldn't know precisely how to do it, because your example with the ecosystem, that would be the same. If you take the ants and separate them from the trees, then of course it would be totally different systems.
Yes.
So this is an unfortunate weakness I only tell to close friends.
Any other questions? Okay. Thank you very much, Professor Jensen, again. I mean, let us applaud. You can turn the mic on. I'm sorry, it really took 1.5 hours almost. Sorry to have taken your time.
Oh, this is wonderful. That's precisely what you need in lockdown, to have these.
Thank you very much. It's very kind of you.
Well, hope to see you all at some point in real life.
Oh yeah. I mean, we would be certainly expecting you here. I mean, there's decent food, and I can take you to some places of historic interest.
Super.
I mean, you are always welcome here.
Thank you. I'll make my way past them as soon as possible.
In Turkish, we say gönülden gönüle bir yol var görülmez, which means there is a path from one heart to the other, which is invisible. So even though it's invisible, we have a path.
Very good.
So
well, thank you for a wonderful
so
event.
Thank you very much to Professor Jensen for this beautiful talk. And I also thank the participants. So see you next Wednesday, same time. Yes, let me also stop recording.